And again, thanks to Harry and these cosmology sessions, I finally realized all this talk about the missing matter and that dark matter is at 45% is 9 times greater than the luminiferous matter. I mean, that's quite a route for universal gravitation. This might be the worst failure of a theory in the history of physics.
I'm not sure about that.
Well, you've got the 4 elements of the ancient Greeks, and that failed, and then they went to 5 elements. And now we're up to some 100 and some odd elements in the periodic table. That was a pretty colossal failure of the 4 element theory. But when you have universal gravitation off by 900%, you really have to just flush it down the toilet.
I find the idea that the particle moves in the direction of higher energy density counterintuitive to a certain extent. But the more I think about it, the more I like this idea, quite frankly.
And, well, if in one direction you have a higher energy density, it means you're closer to the quota to form a particle, which is 3 quanta. If in the other direction, your particle locations, which I call spots, your particle locations only have 1 quanta, who cares if a quantum move in that direction? You only have 2, you're not going to get a particle out of that. Simple logic is, if there's an equal chance of a quantum moving toward a lower density area or to a higher density area, that the net result of that equal chance now, we're ignoring all other forces here. The law of motion is only one factor in all of this. If there's an equal chance, the particles are going to form in the direction where we're closer to particle threshold, which translates to saying in physics talk, higher energy density.
When you say this, I think about electromagnetic attraction, magnetic attraction, attractions of electric charges. That's what comes to mind when you say this. I'm in a different realm, though. You have to appreciate that. I'm in the electromagnetic realm, and you're talking about, in this discussion, you're talking about the gravitational realm.
One of the things in equations of time development, there's only repulsion of like charges there. There is no attraction of unlike charges. Yet, when I use the Binary Mechanics Lab simulator and track the motion of proton particles, I find the electron particles tend to follow the proton particles as if they were attracted. So in other words, the way something actually might look at first sight is not necessarily indicative of the underlying mechanisms, because I was surprised to realize when thinking about this and looking at the equations, I say, hey, all we have is like charges, both plus charges and minus charges. If they're alike, they repel each other. The laws of time development of binary mechanics move them further distance apart. There is no attractive force there at all. However, net, the way it all works out is, hey, in the direction of the positive protons, there are less negative charge. And so therefore, the net effect is that the electrons will tend to follow the protons, because that's the direction of which they get repelled from other electrons most, by following the protons. That's a way to put it in words. Sometimes the way we conceive things in words is not exactly indicative of what the underlying physical phenomena actually is.
Why is it that protons and electrons don't join up?
Well, there's Pauli's principle that 2 particles can exist in the same spot, which is realized in the spot cube, like that yellow electron spot that I showed you. If it's got 3 m quanta in there, those are the circles in the diagrams. If it's got 3 m quanta, it's an electron. You know, there's no way to go to have 2 electrons there in that same spot. That doesn't exist according to the formula of binary mechanics, both in defining the system state and its time development. Now, when we create a neutron, you notice that yellow spot in the spot cube that I showed you was empty in the 42 locations that I showed you of the pro version of binary mechanics proton bit cycle, showing the whole 42 location loop and how there's asymmetries. It's not spherically symmetrical, which agrees with scattering data, by the way, which everyone else in quantum chromodynamics just ignores because they can't explain it. Binary mechanics explains it. If the electron spot is filled in that spot cube, then you have a neutron. So the closest that the electron can get to the proton is to form a neutron.
Protons, at least according to the classical interpretation of the atom, they're right next to each other. Seems they ought to repel, given they're the same charge.
Those three little extensions in the non-spherical proton bit cycle that I showed you in the pro version showing all 42 locations, those little nibs extending out to a neighboring spot cube allow sharing between neighboring spot cubes, so that let's say you've got two protons adjacent to each other in two spot cubes. There's a mechanism, and that gets into the binary mechanics mechanism of nucleogenesis. Okay. Baryogenesis is that if you just throw random bits into the binary mechanics simulator, those random bits are rapidly organized into the proton bit cycle and electron bit cycles. And so that's baryogenesis for the proton bit cycle. So that binary mechanics gives you a tangible, specific data on the formation of protons and neutrons, and as far as nucleogenesis occurs, with the binding of different nucleons together to form higher Z atoms, atoms with higher atomic number, I should say.
The nuclear force, isn't that the one which allows the synthesization of electrons and protons and neutrons to create atoms?
That would be the nucleogenesis part. The baryogenesis part is the formation of protons. What the simulator shows is that if you start out with an initial state of randomly distributed one-state quanta at a certain density, say every 1 in 4, 25% of the locations are seeded with one-state quanta in a totally random fashion, immediately the laws of binary mechanics assemble those into electrons and baryons. And right now, I'm at the stage of developing the software to detect nucleogenesis, in other words, the formation of, say, deuterium and so forth. If the laws are correct, they apply to everything, every known physical phenomena. So if you can even name one physical phenomena which is not accounted for by these laws, I'm not just talking about the law of motion now, I'm talking about all the equations of binary mechanics 1 through 17, then there's something very wrong with binary mechanics. I tried to do that right off the bat. I published the binary mechanics paper written in 1994, 16 years later in 2010. Just right off the bat, I went to get the observatory data on lunar laser ranging because I was trying to disprove binary mechanics. Binary mechanics was saying that with the higher density of the full moon facing the Earth, there's always half the moon illuminated by the sun, right? But when that half of the full moon, half of the illuminated moon is facing the Earth, the moon is closer by some 10,000 kilometers to the Earth. So we got some specific numbers, real observations. I've seen data on what the temperature is of the moon when it's illuminated by the sun's surface and what it is on the dark side. And so that we can really, with the Stefan Boltzmann law and other tools that we have, start to actually calculate these values and show that we get better results than universal gravitation could ever provide us with.